Hey everyone, and welcome. Have you ever stopped to wonder how the simple, flat shapes we draw on paper actually become the solid objects that fill up our entire world? Well, today, we're making that jump from 2 dimensions to 3 to explore the secrets of solid geometry. Let's get into it.
So it really all kicks off with this one simple question. We're surrounded by solid objects, right? But deep down, they all start with something flat. So how in the world do we make that leap from a flat piece of paper to a solid object you can actually hold in your hand?
The magic, it turns out, is all in the stacking. Just imagine taking a single flat shape, say a square or a circle, and then just stacking hundreds, maybe thousands of identical copies right on top of each other. That pile you just made, that creates a solid figure. It's such a beautifully simple idea, and it's what builds our entire 3D world. Okay, so let's start with maybe the most familiar shape of all, the box, or as it's officially called, the cuboid. This is exactly what you get when you stack countless rectangular sheets of paper. Think about it. From a book to a brick, it is the foundation of so many things we use every single day. Now, what if you wanted to wrap that box as a gift? How much paper would you actually need? Well, what you're asking for is its surface area. And the absolute easiest way to think about it is to imagine you could carefully cut the box along its edges and just lay it out completely flat. So when you unfold that box, what do you see? It's just made of 6 simple rectangles, right? You've got a top and a bottom, a front and a back, and 2 sides. So that formula on the screen, yeah, it might look a little complicated, but it's really not. All we're doing is just adding up the areas of those 6 individual faces. That's it. It's just the sum of its parts. Let's make this real. So Mary needs to wrap this Christmas box. We know it's 80 centimeters long, 40 wide, and 20 high. Now she has these square sheets of paper that are 40 centimeters on each side. So the big question, how many sheets is she going to need? Well, after we calculate the total surface area of the box, which, by the way, comes out to 11,200 square centimeters, and then we divide that by the area of one sheet of her paper, we find out she needs exactly 7 sheets. A perfect practical use for geometry, right? And what about all the space inside the box? That's what we call its volume. And this right here perfectly illustrates our original idea. The volume is just the area of that first flat sheet of paper at the bottom multiplied by the height of the whole stack. So simple. Okay, now that we've seen how this concept works, let's build on it. What happens if we stop stacking rectangles and start stacking circles instead? Well, we get a cylinder, like a can of soup or a roll of paper towels. A cylinder's curved surface has this really neat secret. If you could peel the label off a can in one perfectly flat piece, what shape would it be? You guessed it, a simple rectangle. And the area of that rectangle is just its length times its width. Now the width is just the cylinder's height, h. And the length? Well, that's the distance all the way around the circle at the top. Its circumference, which is 2 times pi times the radius. Simple as that. And just like we saw with the cuboid, the volume follows that same beautiful logic. It's the area of the base, which for a circle is pi times the radius squared, multiplied by the height of the stack. Base area times height. It just keeps working.
So far, we've been all about stacking. But there's actually another way to create a 3D solid from a 2D shape, and that's rotation. This brings us to the super elegant cone. I want you to picture this. Take a right-angle triangle, tape one of its straight edges to a string, and then just spin it really, really fast. The shape it traces out in the air is a perfect cone. And this little thought experiment helps us understand all its properties, like its height, radius, and this new measurement we call the slant height. The area of that curved surface is given by this neat formula, pi times the radius times the slant height, which we call L. This is basically the amount of paper you'd need to make one of those classic party hats. And here is a great example. A corn cob. It's basically a cone, right? So if we know its dimensions, and we know that each square centimeter holds about 4 grains of corn, can we actually figure out how many grains are on the whole cob?
Yes, we totally can. By calculating the curved surface area, we find there are approximately 531 grains of corn on this cob. It is absolutely amazing how geometry can answer questions just like this. Now for the volume of a cone. Oh, this has a fantastic relationship. If you have a cone and a cylinder that have the exact same base and the exact same height, a simple experiment shows something truly incredible.
It takes exactly 3 full cones of sand to fill up the cylinder, which means the volume of a cone is precisely 1/3 the volume of its corresponding cylinder. It's one of the most elegant relationships in all of geometry, for sure.
Our final shape is maybe the most perfect of all, the sphere. And just like the cone, we can imagine creating it by rotating a 2D shape, this time by spinning a circle around its diameter. The surface area of a sphere holds another one of these stunning secrets. Imagine wrapping a string tightly around a ball until it is completely covered. If you then unwound that string and used it to fill flat circles with the same radius as the ball, you'd find it perfectly fills exactly 4 of them.
And this leads to one of the most beautiful formulas in mathematics. The surface area of a sphere is simply 4 times the area of a circle with that same radius. 4 times pi r squared. Beautiful.
So, from stacking paper to spinning triangles, we've basically unlocked the formulas for the fundamental shapes that make up our world. And these aren't just abstract ideas, you know? They are the building blocks of everything, from planets all the way down to packaging. You know, the world looks a little bit different once you understand the geometry that's hiding in plain sight. So, my question for you is, as you go about your day to day, what cones, cylinders, and spheres are you going to notice that maybe you never even saw before?